session. So we will continue ahead with work power energy today. We have discussed quite a few things about calculation of work done by a force, right? In case of the force being a constant force or a variable force, etc. And we will continue from that point ahead today. So this is work power and energy session number 3. So we have so far understood how to calculate work done by a force as the path integration of the force over displacement from initial to final position. But we've also seen that this reduces to F dot S, or a simple scalar product of force and displacement, when the force is constant, when F is constant. Whereas otherwise in general, we have to rely on the integration part. Okay. So today we will start by understanding the relationship between work and kinetic energy. Okay. And to that end, we will start with the statement of the work kinetic energy theorem. So basically what happens is, if there's a body on which number of, so suppose this body is moving with the initial velocity u, and there are number of forces acting on it. Let's say there's a combination of many forces, F1, F2, like this. Okay. And after some time we notice that, okay, the body's motion has changed from this to this. Okay, so it's gone from this kind of motion to going along some kind of path like this. And so this is initially, and this is the final state after some time. So during this time, the total work done by the forces acting on the body, the net algebraic sum of the work done by all the forces acting on the body, that results in a change in the energy of the body, which is associated with motion, and that is called the kinetic energy. So the statement of the work kinetic energy theorem is that the net work done, okay, by all forces acting on a body, this thing equals to the change in its kinetic energy. Okay, and we'll come to the formula for this also, and how we describe kinetic energy and all that. So the net work done equals to the change in kinetic energy. This is the statement of the work kinetic energy theorem. I have not finished explaining, Rishi, so like it's not a question of explain again. Okay, I'm not finished explaining the work kinetic energy theorem. Let's listen to it through, then you can understand again. Okay, so here the net work done, this quantity, okay, this is equal to the algebraic sum of work done by all the forces acting on the body. So in my example, if there is F1, F2, F3, like this, up to n number of forces acting, this is equal to work done by the first force plus work done by the second force, up to like this. Okay. Or further, when we elaborate, this will become integration of F1 dot ds for the first force plus integration of F2 dot ds for the second force, till we cover all the forces that are acting on the body. So we have to algebraically sum up, because remember, work is a scalar quantity which can be positive or negative. So when we say net work done as the sum, it means algebraic sum, because some of the forces might be doing positive work, some of the forces might be doing negative work. So that is the left hand side of the equation, and the right hand side is the change in kinetic energy. So I'll come to that, but just make a note of this first. Okay. So this earlier part, work done by a force, you've seen. Now just note down this section here. Then we'll understand the right hand side of the equation also, that what is meant by the change in kinetic energy. So this is the relationship between work and kinetic energy. Uh, you mean ds, the displacement? Yeah, because it is a displacement of the particle, na, where the force is acting. So when we are discussing about particle dynamics now, like I had explained earlier, that we are talking about the force acting on a body which is translating or on a particle. So the displacement is the same for all the forces. It's only in rotational mechanics that it becomes a little bit more complicated. That I was explaining to you in the first lecture. So when we are talking about particle dynamics over here in this chapter, we need not worry about what these DSs are. They are the same. They are the displacement of the body in each case, because the displacement of the body is the same as the displacement of point of application. In any case, when we do numerical examples, we will understand this better. The important thing is that we know how to calculate the work done by one force, the second force, the third force, and so on and so forth. So like that, we will calculate the net work done as the sum of the work done by all the forces. But of course, by sum, we mean algebraic sum. So their algebraic sign, whether it is positive or negative, should be included. Yeah, just write this down, and with examples, you will understand this in detail. Okay, just write down the statement of this work kinetic energy theorem, Ayush. Okay. Then when we are doing the examples, it will become clear to you automatically. Okay. Now right hand side we have change in kinetic energy. So this quantity delta Ke, this is the change in the kinetic energy of the body. Now like work, kinetic energy is also a scalar quantity. So change in any quantity is final value of it minus initial value of it. Okay. So in the case of kinetic energy, the final kinetic energy is half mv square, where the final speed is v, and the initial kinetic energy is half mu square. Okay. So here m is mass of the body, and v is the final speed. Okay. Or you can even say it is the magnitude of the final velocity. Okay. Speed and magnitude of velocity is the same. U is the initial speed. So the change in kinetic energy is defined in that way. So this thing is the change in kinetic energy. So this is a theorem that we'll be using for solving dynamical questions using the concept of work done. Okay, that the net work done will give us the value of the change in kinetic energy. So when I explain this with examples next, it will become clear to you what we're doing here. Okay, so hope you've written this down. Let's understand a quick example. So supposing we have a situation like this now. There is a rough surface like this, horizontal rough surface, and there is a block that is lying on it at rest initially. So there's a block of mass m which is at rest initially at this position A. Okay. And this surface has some given coefficient of friction, suppose that is some 0.2, and the mass of the block is 5 kgs, and we'll take acceleration due to gravity as the standard value, 10 meters per second square. Okay. Now, a constant horizontal force of magnitude, let us say 25 newtons, starts acting on it, on the block. Okay. And we want to find its speed v at the instant when it has moved through a displacement of magnitude, let us say, whatever, let's say 10 meters. By the time it has moved through a displacement of magnitude 10 meters, we want to find out how much the speed is. Okay. Okay, I wish I will come back to that. Let's finish this problem first. Okay. So what we have to understand here is that, of course, we can solve the problem by first finding the acceleration and then use kinematics. So we have one method like this. Method one could be that solve the free body diagram and find the acceleration. Okay. And then use kinematics to find the speed from the given, from the acceleration that we have calculated. Okay, so there we can do this two-step process. But now we have the other method, and that is going to be more effective over here, which is the work energy method. Or more precisely, we can say that way it is by application of work kinetic energy theorem. Okay, whose statement we know is that the net work done is equal to change in kinetic energy. So from this we will find out what we use. Okay, so let us look at method 2 over here, how we will apply the second method. Okay, just make a quick note if you want of this, but you don't really need to make detailed note. Just make the the values which are given, make sure you've written them down. The mass, the coefficient of friction, the situation, and all that. And what has been asked, that when you are continuously applying a horizontal force of 25 newtons, what is the speed after a displacement of 10 meters? Okay, now let's see how we will apply the work energy theorem here to get it. Okay, so let's understand what's happening here. So the block is at rest initially, okay, and we start with the application of the force of 25 newtons. Okay, so the moment we start applying that force, the block will start displacing. You'll understand that because when you calculate, the friction will be less than 25 newtons, and the maximum friction. So this external force we are applying horizontally, that is of 25 newtons. Okay, and we've already seen that the mass of the block is 5 kgs. The coefficient of friction was 0.2. So the other forces you can see that are coming into play is weight and normal reaction balancing each other, vertical forces हैं, so they balance each other, but that will create contact between the surface and the body. So N is equal to mg, which will become how much now here, 50 newtons, because we are taking g as 10. Okay. So the kinetic friction that will be acting will be mu n, so that will become how much, 0.2 into 50, so that's 10 newtons. So the amount of friction acting is only And the maximum friction is only 10 newtons. So we know that it's not sufficient to prevent slipping, and the body will start slipping, and this kinetic friction will start acting on it. Okay, so now we will not get into acceleration. What we'll use is work energy concept. So iska initial speed 0 hai yahan pe at the point A. Now let's say after some point time it reaches this position here. Let's say this position is B, where it's reached a speed of V. And we are also seeing that the displacement from here to here is the value that we have to solve for, which is the displacement of how much? 10 meters, I think I had taken. This is S is equal to, I'll just go back to the question, through a displacement of 10 meters, 25 newtons, 0.2, all that is there. Okay. All right. So ये जो है 10 meters का displacement है. Now we will use the statement of the work energy theorem, the work kinetic energy theorem. The net work done is equal to the change in kinetic energy. Okay. This is the statement, and we'll use it for the displacement from A to B. Okay. So now the net work done will be the work done by the force F plus the work done by friction plus the work done by mg plus the work done by normal reaction. Okay. Now the work done by the force F, you can see, will become plus Fs. Work done by friction will be minus kinetic friction into S. The work done by mg and normal reaction will be 0, because you can clearly understand that n is perpendicular to displacement. Okay. mg is perpendicular to displacement, so it's not doing work. Okay, this work done is kinetic friction is at 180 degrees to the displacement, it's opposite, and so that's why it's becoming minus, and this is becoming plus Fs, because theta is 0, here theta is 180 degrees, so it's becoming minus Fs, like that. So this is the net work done. So how much is the net work done becoming now? It is becoming 25 into 10, okay, minus kinetic friction, which we saw is 10 into 5. So it's 250 joules minus 50 joules. So that's plus 200 joules. This quantity is my net work done. Okay. Now the right hand side of the equation, change in kinetic energy, ye kitna hoga? That is going to be equal to half mv square minus half mu square. Now u is 0. So I'm getting the relation that this is going to be half into the mass of the body, which is 5 kg, into v square. Okay, so that is my change in kinetic energy. And this is the net work done. So now we have to equate the two. Okay. So net work done is equal to change in kinetic energy. So 5 by 2, or let's write work done on this side. So 200 joules, that is the net work done. Okay, that is equal to 5 by 2 v square. So v is coming out to be how much now? Square root of 80. So we'll get that. Or so next step we will get that. Okay. So this is the work kinetic energy theorem method. Okay. Yeah, that's correct. We can express it that way also. Twenty by root 5. That's correct. Okay. So I'll take you back to the previous section, but just understand how we have applied this method over here. So from A to B, we are applying the statement of the work kinetic energy theorem. And okay, we will hope this question was clear and you have understood the calculation of work done in for each of the forces. Now, okay, how we calculated the work done for F, how we calculated the work done by friction, and why normal reaction and mg was doing zero work. So this was a simple problem in that matter. Okay, now just to illustrate, now we will also solve this by the method one. What if we did not use work energy? Method one was using free body diagram and kinematics. How we would solve that? You'll see, we'll come to the same answer. So first thing is, when you make your free body diagram, you will write your equation for it. That इसमें net force क्या लग रहा है? In the direction of this thing, now the motion, the net force is F minus kinetic friction. That is equal to ma. Okay, normal reaction is balancing mg, and kinetic friction is equal to mu n. So ultimately, when you substitute this here, we get this F minus mu mg is equal to ma. So from this, we will solve this. So this is 25 minus this was 10. This will become 5a. So we'll get the acceleration as how much now? 3 meters per second. Right. So now from that, we can find out the, using the kinematics, we can find out the value of speed. Okay, initial speed is 0, final speed we want to find out. So which relation you will use? V square is equal to u square plus 2a. So you do that, we'll get the answer. Oh, wait a minute. I think I made a mistake in the calculation. This is, people please make a correction here. No? S is this thing, 10 meters. So work done by friction is different. Okay. Just, should I point it out? No? Nobody pointed out also. वर्क डन बाय फ्रिक्शन कितना आ जाएगा? 50 नहीं आएगा ना, 100 आएगा ना, -100. See here, we'll substitute this as 25 into 10, so that's plus 250. That's done. Okay, but what about this? This is becoming minus of friction is 10 newtons. We saw here earlier, friction is 10 newtons into the displacement of 10 newtons. So this is minus 100. So this is minus 100. So the net work done is not 250. It's not 200. It is 150 joules. Okay, 150 joules is the net work done. So the change in kinetic energy. Okay. Now in this u is 0, so that becomes half mv square. So that is okay, 5 by 2 v square. So you'll get a different value of v actually. That root 80 was not correct. You'll get a different value. Okay. So that is the advantage of checking with the other method. So we are able to find out that there is some calculation mistake that has happened. Anyway, so abhi kya karenge? Net work done is equal to change in kinetic energy. So once again, 150 is equal to 5 by 2 v square. So v will come out to be how much now? Root of 60. Or you can write this as 2 root 15 meters per second. Is that correct? Please check the calculation properly, everyone. Okay. You should be alert in class. Na? If I've made some calculation mistake, you should tell me. If I've substituted the wrong value, you should tell me. You can see that I had substituted S as 5 instead of 10. Okay. So anyway, make sure you incorporate this correction. Okay, so it's this much. Now let's come back to this kinematics method. So acceleration itna ho gaya mera. Now u is 0, and after a displacement of how much is it? 10 meters. We want to find out the v. Okay, and we know the acceleration. So we'll use v square is equal to u square plus 2as. So here v square is equal to 0 plus 2 into 3 into 10. So there you are. You will get the same thing, that v is root 60, or that's the same thing as 2 root 15. So that's actually going to be very nearly 8 meters per second, slightly less than 8 meters per second. Okay, so people hope this question is clear. Now see, the next example I will show you now is something more interesting, where you will see that work energy can give us the result, whereas Newton's laws cannot give us the result. Okay, suppose we have a situation like this, where we have a surface which is sloping like this. It's not a regular slope, it's an irregular slope like this. So it's not like a regular inclined plane, it's not a straight inclined plane, but it is frictionless. Okay, and we know that the height difference between this point here and this horizontal level is h. This is known to us. Now a particle is just about released from rest over here. So from the point a particle is just released from rest. So it comes sliding down like this because of the slope and gravity acting on it. So by the time it reaches here, it has some speed v. Okay. So this is a smooth surface, frictionless or smooth surface. Okay. So we want to find, so a particle, let's say mass 1 kilogram, whatever, is released from A at rest. Okay. It slides down the smooth surface. Okay. Given, suppose that this h is equal to, let's say, 20 meters. So we want to find, first of all, the work done by each of the forces acting on it. Okay. From A to B, we want to calculate the work done from A to B. Each of the forces, how much work is done by them. That's the first thing. And then from that, we want to find out the speed at B. Find V, that is its speed at the point B. So now in this problem, you'll realize that work energy gives you a solution to a certain situation where Newton's laws would not give us the solution. We don't have the other method of using kinematics because it will have a non-uniform acceleration. No? It's not a straight inclined plane. So the acceleration is varying from point to point. So we don't have the option of using kinematics, but we have the option of using the work kinetic energy relation, and it's a one-line solution actually it will give you, and you'll see the advantage of the work energy theorem, or in this case, the work kinetic energy theorem. So just try this out, people. Tell me the answer quickly. Should not take more than a minute. Give me the answer for V in meters per second fast, okay? And the work done by each of the forces in joules. Yeah, anybody got the answer, people? Yeah, anybody got the answer for? Okay, sorry. Okay. So what all forces are acting on the body as it is moving? See, the forces acting on the body are, at any point of time, there are only two forces acting. One is mg and the other is normal reaction. Now the thing is that you'll understand that normal reaction keeps varying, but mg remains constant. यहाँ पे है तो normal reaction ऐसा है. At every point the normal reaction is different. By the time it comes here, normal reaction is then in this sort of direction. By the time it comes here, normal reaction is almost like this. Okay. But mg is constant. Okay. So here this is like this. It's always the displacement will be along the tangent, okay, at that given point. So it will be perpendicular to normal reaction. Okay. So for work done by normal reaction, we will have to use this relation, but that will be 0 because n is perpendicular to the differential displacement at all points. Okay. Whereas as far as work done by mg is concerned, we have to just use this mg dot product with displacement because mg is a constant force. I'll just check the answer. Just give me a moment, guys. Okay. Whereas normal reaction is a variable force. Okay. So to calculate work done by mg, we just need to see that okay, A to B, what is the displacement? A ऐसा point था, B ऐसा point था. So the displacement is something like this. So we okay. Yes, very good, Kunj. That's correct. Okay. So use this method. Now, once you got the work done by mg, work done by normal reaction, you can see 0. So net work done is that much only. You know, whatever you got for work done by mg in joules. So that is equal to the kinetic energy because again it's starting from rest. Okay, very good. G is 10 beta. Xavier take G as 10, so it's fine. Okay. So see our displacement for mg, no? I mean the displacement between A and B is this vector. So ये वेक्टर का इंटरेस्टिंगली मुझे हॉरिजॉन्टल कंपोनेंट पता भी नहीं है कितना है ना. It is some x which I don't know, but vertical component पता है, and that's all that matters. Okay. So S is equal to some unknown x I cap, but minus h j cap, no? And that is all that matters actually. Ki how much the y component is, because what I'm going to use this as for work done by mg. Now mg is minus mg j cap, na? It's acting in the negative y direction always. So from this now I can see that work done by gravity, which is mg dot s, ये कितना आ जाएगा? It will be coming as mgh. The two minus signs will cancel. So this term will actually come out to be mgh. This is the work done by gravity. Okay. So finally what we'll get, that work done by gravity is going to be, how much was the mass we had taken? I think it was 1 kg. G will take as 10. Okay. And h was 20. So 1 into 10 into 20. So 200 joules. That is the work done by gravity. Whereas the work done by normal reaction is 0. So that is my first part's answer. Now the second part is here only. I have to just calculate the net work done is the change in kinetic energy. So you can see at A, U was 0, and at B, the speed is V. So net work done is 200 joules, and that should be equal to half mv square. So V is this time becoming square root of, m is 1 kg, so it's becoming square root of 400. Right. H is equal to 20 meters. So interestingly, we are getting V as 20 meters per second. Okay. Whole number value, nice. Okay. So this is the process of using the work kinetic energy theorem. Okay, there will be more complicated things also we will see in this, but the statement is this much only. It's just applications with more number of forces, more techniques for calculating work done. But the statement and the process is this much only. Okay, so people, hope you have understood this question and it's done. Okay. Now coming back to work done by variable forces, we will look at some more examples of that. Okay. So work done by a variable force by the formula, or rather from the definition, path integration. Let's look at some more examples of this. So we had seen the one-dimensional example of work done by spring and all that. Okay, but now let us look at a situation like this where this is happening in 2 dimensions. So this kind of situation gets very interesting. So let's say we have a particle in a 2-dimensional plane, okay, moving from the origin here to some point A, let's say, which has coordinates, whatever, some coordinates, let's say uh, A comma 2A. Okay. Now a particle of, let's say, mass 2 kgs, okay, moves in a two-dimensional xy plane, okay, under the action of a variable force which is given by this relation, that F is equal to, let us say it is 3x square I cap plus 4j cap, okay, where x comma y is the position of the particle, okay, and F is in newtons when x and y, or rather in this equation x is in meters. Okay. So this is the force acting, the variable force acting on the particle when it is at a certain coordinate x comma y. So the x component depends on the x coordinate, whereas the y component is constant, as you can see. Okay. Now we will see that this particle is moving from the origin to the point A, but via two different paths. Okay, there is a situation where it can move from the origin to the point E, which I've shown over here. So one possibility is that it can move in this path that I'm showing you next, that it first goes from the origin along the x-axis to this point here, and then it makes a 90-degree turn and goes along the y-axis, and finally it reaches. So this is the first situation. So let's say this is path 1. Okay. And on the other hand, it can also do that instead of this path, it goes the other way. It first goes along the y-axis from the origin, but by path 2. So in each of these paths, now we will calculate the work done separately. Okay. So when this particle moves from the origin to the point E, okay, we have to find the work done by this force F, okay, for path number 1, which I showed, and secondly for path number 2. Okay. And actually, instead of this, now let's take numerical values. So the coordinates are, let us say the coordinates are 2,4 meters. They are 2,4. X is in meters, Y is in meters. I don't think I'll refresh the screen. Okay. So is the question now clear to all of you? Trisha, is it clear now? Are you able to see the screen clearly, beta, Trisha? Okay, I'll refresh the screen. What about now? Is it clear? Okay, okay. Sanskruti, is the screen clear for you now, beta? Okay, okay. Okay, now just take down this question. We'll understand how to solve it. Okay. Okay, so let's see how we will solve this next. Okay. So let's work out the first part. So what is happening is we are going first along the x-axis, right, from the origin to some point on the x-axis, and then we are turning such that next we start moving parallel to the y-axis till we reach our destination point, which is A. So for that entire path, now we have to now calculate the work done. So this entire path number 1, we will divide it into two parts. We'll say that this point, let us say, is some in between point, which is B, and then from here we are going to A. So this point was 2, 4. So that means this point must have been 2, 0. Okay. So for this journey by path 1, we will first calculate the work done in going from the origin to the point B, and then from the point B to the point A. Okay. So work done by path 1, we'll calculate it as work done from O to B plus work done from B to A. Okay. So how to calculate work done from O to B? So for that we have to do this integration f dot ds from the origin to the point B. Okay. So now obviously f is a variable force. So let's look at this. So when the particle is at some general point like this, now, where its x coordinate is some x, but y coordinate is 0. Okay. Let's understand how much force is acting on it. So at this point of time, we can see that the force acting on it will have both components. Now, when we look at the expression of force, we'll understand why. Because the general expression of force was what? It was 3x square I cap plus 4j cap. ऐसा था ना? This was the general expression for force. So now specifically while going from O to B along the x-axis, okay, at any point x comma 0, okay, where x is obviously greater than 0 but less than 2 along the path OB, along this path, what is happening? The force at that point is, just substitute the coordinates. So x को मैं x substitute करूँगा, y को 0 substitute करूँगा, but force will come out to be this much. Okay, and now more importantly, from that point, how the particle is moving? It's moving along the x-axis only. So the differential displacement ds वो कैसा होगा? वो ऐसा होगा. We'll just have an x component. So ds will be a vector like this. Okay, which will just have an x component. It will not have a y component because it's moving along that path, no, OB. Okay. So now my work done from O to B, which is integration of f dot ds. When I substitute f and ds over here, what I will get? I will get the product of the x components. So that is 3x squared dx. Product of the y components is 0 because this ds does not have a y component. And at the point O, my x coordinate is how much? 0. And at the point B, my x coordinate is how much? It's 2. So this will become 3 into x cubed by 3. Okay, from x equal to 0 lower limit to x equal to 2 upper limit, definite integration. So this will tell me the calculation of the work done in half that journey, or you can say part of that journey. The first part, which is along the x-axis. Okay, so this is coming out to be how much? This is coming out to be 8 plus 8 joules. This is the work done from O to B. Okay, so now similarly, we will look at the work done from B to A. Okay, so for that also we'll integrate f dot ds, but from the point B to A. So for that we'll see that while going on that line, at any arbitrary point, what are the coordinates? The x coordinate is fixed, 2 हो गया, y coordinate vary हो रहा है. Okay, so now also the force will have two components. Okay, at this point also the force will have two components. But now the other thing is that the displacement will be along which direction? It will be along the y-axis. यहाँ पे displacement ऐसा होगा. So along the line BA, okay, at any point 2 comma y, the force will become, now substitute x as 2, so 3 into 2 square I cap plus 4 j cap, or the force will be 12 I cap plus 4 j cap. Okay, and the displacement will be dy j cap this time. There's no dx this time. Okay, so we will substitute these two here and calculate the work done from B to A. And then we will substitute them over here. So that will give us a net work done in the path number 1, going from O to B and then going from B to A. So just substitute these and calculate the net value now. So try out the second integration yourself. The first one I've already done for you. So write this down and then work out this WBA. See how much you're getting in that in joules. Okay, so hope you worked this last part out now. So यहाँ पे देखो, when we substitute this here, the work done from B to A, this f dot ds integration this time from the point B to the point A, ये कितना हो जाएगा? It's the dot product of these two. So it's a very simple thing. It is 4 dy. 12 into 0 plus 4 into dy. So that's 4 dy from the point B where the y coordinate is how much? 0 to the point A where the y coordinate is becoming 4. So it is becoming 4y from y equal to 0 to y equal to 4. So it is becoming 16 joules. So this work done is 16 joules. Okay. So now with these two work done in place, now we can say that, okay, what is the work done in path 1? Okay. Going from the origin to the point A, it is the sum of the work done first going along the x-axis from the origin to the point B, and then going along the y parallel to the y-axis from B to A. So ये कितना हो जा रहा है? This one was 8 joules and this one was 16 joules. So okay, the total work done is becoming 24 joules. So this is how we'll conclude this part. The work done in path 1 by this force is this much. Okay. So this is the first part of the question, the work done in path 1. Now using the same method, now I want you to calculate the work done in the second path. Remember how the second path was? You were first going along the y-axis and then parallel to the x-axis. So use just the same type of application to calculate the work done in the second path, and you will see something interesting over here. Hello. Yeah, anybody has calculated, please send me the answer na, for the second part. The work done in path number 2. That was a different diagram where it's first moving vertically along the y-axis. Okay, and then parallel to the x-axis from that point on the y-axis to the point E. Yes, very good, Kunj. You should be getting the same value. Okay. So the path is different and it will be doing different amount of work, first going up, different amount of work going horizontally then, but the total work done will come out to be the same. Okay, so that's the interesting thing. So let's take a quick look at this now. So the second part, so if I'm now going along this path from the origin to this point first, okay, let me call this point C or something, and then to the point A. So this point is having coordinates 0, 4, and this is our path 2. Okay, so the work done in path 2 will be equal to work done going from O to C plus work done going from C to A. So work done going from O to C, let's calculate how we'll get. So when you are at any point like this, the coordinates of that point are 0, y. Okay. So immediately you will see that the force is only having a y component, because the force was like this. It was 3x square I cap plus 4j cap. Okay. So at some point 0, y from O to C, you can see that the force will just be 4j cap because the x coordinate is 0. So at this point of time, the force acting on the particle is only like this. Okay. And the displacement is also in the same direction. Okay. So ds is dyj cap. Okay. So work done from O to C is just becoming 4 dy integration from O to C. So that is y equal to 0 to y equal to 4. Okay. So ultimately you will get this as 16 joules. Y equal to 0 to, so this will be our plus 16 joules. Okay. So this time the first part of our journey is giving us 16 joules. Okay. And then next thing, when we calculate the work done from C to A, so you are at some kind of general point like this where your x coordinate is varying, your y coordinate is fixed at 4. So the force will now have a general value like this, but your displacement will be along the x axis now this time. Okay. So at a general point, x, 4, okay, going from C to A, the force is this much. Okay, but the displacement is dx I cap. So work done that becomes your 3x squared dx from C, where x is equal to 0, to the point A where the variable x is 2. So this will become 8 joules. Knew that this will come out to be 8 joules. So this is one case where we are getting something interesting. By the two different paths, the work done is coming out to be the same. Okay. So in fact, this thing is pretty important, that in which case the work done is the same, in which case the work done is different. So we're going to see a whole definition based on this, something called conservative forces. If the work done by a force does not depend on path, but only depends on state or position, that is, if I'm going from the same initial state to the same final state by any different path, any and every path, the work done should be same every time. Then such a force will be called as a conservative force. Such a force will be defined as a conservative force. Whereas if the force is not same in the two cases for two different paths, then if the work done is not the same, then the force is called a non-conservative force. So there is a distinction, or there's a classification of forces on this kind of basis actually. If the work done by a force is independent of path, it depends only on the initial and final state, then it is classified as a conservative force. We will see that definition soon. Whereas if it is dependent on the path, that means the same initial and same final point, but two different paths will give you two different amount of work done, then the force is classified as non-conservative force. And that's a pretty important concept in what we're going to learn ahead. Conservative versus non-conservative forces. Okay. Now, before we come into conservative and non-conservative forces, we'll look at another example of this. Okay. Now, this time, let's say we have the same situation, a particle in a 2D plane. Okay. In the XY plane. And a variable force. But this time that variable force is given by this relation. It is, let's say, 2x I cap plus x into y j cap. Okay. So it is this kind of a relationship where the at a point x comma y. Okay. X is in meters, y is in meters. The force is in newtons. Okay. And we will take a similar kind of situation that we'll take two different alternate paths for a body to move from, again, a similar thing, the origin to some kind of point like this. Okay. And we will show that it's always possible that the work done is path dependent also. It need not always be path independent. It really depends on the type of force we are dealing with. So let's say this is our point this time, which is, let's say, 2 comma 1 in meters. And once again, are two different paths. This is one path. Okay. This is our second path. So the particle on which the force F acts is moved from O to P. Okay, find work done by F for path 1 and for path 2. Okay. So you can start working on this, apply the same type of method that we saw earlier. I'll put up the calculation soon. So Kunj, have you calculated? Anybody done the calculation of work done for each of these? Yes, you're getting different work done, no? Okay, I will just verify the values. So this is an example of what we will later see, na, is a non-conservative force, because this may has out there. So anyway, let's do directly for path one first. Okay, so let's say this point is A now and this point is B now. So work done by path one, इसको हम करेंगे as work done. Sorry, we'll do it as work done from O to A plus work done from A to P. Okay, so now when you are at a point like this, your A का coordinates कितना है 2,0 और यहाँ पे coordinates is x, 0. Okay, so what you can see is your force is just becoming 2x I cap. F is 2x I cap because your y coordinate is 0, and your displacement is dx I cap at this point. Okay, so for this part, the work done will become 2x dx from x equal to 0 to x equal to 2. Okay, and likewise we'll come for the AP part also. Now in the AP part, you can see that you are at a point like this, जिसका coordinate कैसा है? The coordinate is 2, y. So the force has a general value. Okay, so the force has a general value which is 4 I cap plus 2 y j cap, whereas the displacement is along the y axis. So this is dy j cap at this point. Okay, I'll just calculate. Okay, so this one will become like this. For the part AP, f dot ds का जो integration है, इसमें f कितना होगा? It will be 4 I cap plus 2 y j cap, and ds is dy j cap. So this will become 2y dy, and this time going from y equal to 0 to y equal to 1. So this is x square going from x equal to 0 to x equal to 2 plus y square going from y equal to 0 to y equal to 1. So I'm getting the work done as 3 joules. As 5 joules. 4 plus 1, 5 joules. This is the work done by path 1. Okay. You can just verify my method. Since some of you are getting different values, Kunj, you have got the same. Okay, so I think it must be correct. Okay. Now let's come to the second one. Okay, and the second path, what is happening is that you are going first from here to here like this, and then like this. Okay, so when you are at a point like this, the coordinates are 0, y. Na? Okay, so the force only is 0. You'll see. X coordinate अगर 0 है तो यहाँ पे force ही नहीं है. Okay, so going from O to B in path 2, there is no work done. Okay, then when you're going from B to P at this point over here, now you're at a point like this, जिसका coordinate कितना होगा? The y coordinate is fixed at 1 and the x coordinate is varying. Okay, so you will have some force which will be given by 2x I cap plus x j cap. Okay, but now your displacement is going to be along the x axis. It's going to be dx. Okay, so when we do this calculation, work done in path 2 is work done from O to B plus work done from B to P. So this will be 0, whereas this one will be dot product of these two. So that is 2x dx going from x equal to 0 to x equal to 2. So this will again give you your 4 joules. Okay, so इस बार क्या होगा? In the path 2, the net work done only is 4 joules. It's plus 4 joules, whereas in this it was plus 5 joules. Okay, so I've skipped some of the calculations. I've done them mentally, but just try them out yourself. Like you can see this one will be 0 plus x square, and the limit is from x equal to 0 to x equal to 2. That's how I'm getting 4 joules as answer. Whereas the work done in path 1, I'm getting the answer as a total of plus 5 joules. You can see two different paths are giving you two different amount of work done. Whereas in the first example we had seen earlier, it was the same amount of work done by both the paths. So this is bringing us to the very important concept of conservative versus non-conservative forces, which we will discuss about next. Okay, people, hope the calculation for both the parts is clear. Please go through it very carefully. The integrations, the substitutions of the coordinates and everything. Make sure you understood each and every step. It can be a bit tricky, these type of questions. Okay, this is like proper JEE level questions. Okay, so make sure you understood each of the steps. If there's any doubt, let me know. Okay. So Hitanshu, this is clear now. You understood the calculation, na, beta? Okay, so that brings us to our definition of conservative and non-conservative forces. Okay, actually indirectly we've both seen two examples of them, but let's understand the proper definition now. Conservative and non-conservative forces. So this is something very important and critical in work power energy applications. So as we were discussing, if the work done by a force is independent of path, then it is called a conservative force. Independent of path ka matlab kya hai? That it only depends on the initial and final position. Whatever path we take it from, if we take it from a point A to a point B by any path, not just two individual paths, but any path arbitrarily, any randomly chosen path, as long as I'm going from point A to point B, the work done should be same every time. So that is conservative. Whereas if the work done is not going to be same every time, so that means it depends on what path I'm taking. It is non-conservative. Okay. So if the work done by a particular force is path independent, that is what we mean by path independence. That is, it depends only on the initial and final position. Okay, position or whatever we call it, state. Then it is classified as a conservative force. That is the meaning of conservative force. And already in the forces we have discussed about, there are many examples of it. No, it need not be a straight line, beta. Ayush, I will show you that. It can be any arbitrary path also. Like earlier today, remember we were calculating work done by weight for a random, inclined surface, which is not a straight inclined surface, a curved inclined surface. So it can be a path like that also. So, between my point A and B, if this is my initial state and this is my final state, my path could be like this, any random path like this, or it could be another path like this, or it can be another path like this. Okay. It could be something strange like this also. It can be a combination of many straight lines. It does not matter. All paths, whether it is path 1, 2, or 3, be same always. Between the same 2 points, it will be the same. Then it is called a conservative force. Okay. And non-conservative is just vice versa of this. If it is path dependent, that means in the different paths is going to be different. If these work done were not the same, then it is a non-conservative force. So then we say it is path dependent. Okay. Then it is classified as a non-conservative force. Okay, this is something pretty standard from NCRT to any reference book. You will see the same definition is there. Yes. So basically, what we mean by saying path dependent means that the work done by different paths will be different, but between the same 2 points, same initial and final state, but different paths. Okay. It will be different. So in that example over there, okay, going from A to B, that example, if the work done by path 1 is not equal to work done by path 2, then it is non-conservative. Okay, people, so hope you understood this definition. Now, there are a couple of more important things about conservative and non-conservative forces. Okay, we'll discuss about that. Now, not only the work done, I mean, the work done by the conservative force is path independent. Another important thing is, okay, for a conservative force, the work done by a conservative force in what is called a round trip. Round trip का मतलब क्या है? If your path is a closed loop, like you started from some point E, and by whatever path you came back to that same point E, this is called a closed loop. Okay, so if the work done by a conservative force in a closed loop path, okay, so this thing in short form we call it round trip. Round trip का मतलब क्या है? You're coming back to the same position, must be zero. By definition, conservative force, because the work done is path independent. So if I'm coming back to where I started from via a closed path or via a closed loop path, then the work done must be zero for the conservative force. Whereas if the work done is non-zero, then that means the force is non-conservative. Okay. Work done in a closed loop path is non-zero for a conservative, for a non-conservative force. So not only the definition is important, the property about closed loop path is very, very important. That is the first important property you should know after the definition of conservative and non-conservative. Agar conservative force hai, then in a closed loop path, you're coming back to where you started from, the net work done by the force must be zero. Agar non-conservative hai, it will be non-zero. Okay, people, so hope you understood these definitions. Okay. So, coming back to the earlier examples we were doing, you can see that the first force that we had taken, the variable one, it was a conservative force, and the second one is the non-conservative force. Okay. So we will see more examples and applications of conservative and non-conservative forces in the next lecture. I will be scheduling an extra lecture on Sunday for you because of the lecture we missed on, when was it, Tuesday, I think. Okay. Yeah, I think day before yesterday, right? We missed one lecture. So I will be scheduling it on Sunday. Just give me some time. By Saturday, I will adjust the timetable so that I can give you the timing of the lecture. Okay. So remember, in addition to your DPT, this Sunday you will also have a lecture with me. That's it for today's session, people. Wish you all the best.